This is Chapter 13, Problem 34. The problem reads, for Part A, what is the minimum speed relative to the Sun necessary for a spacecraft to escape the solar system if it starts at the Earth's orbit? Part B asks, Voyager 1 achieves a maximum speed of 125,000 kilometers per hour on its way to photograph Jupiter. Beyond what distance from the Sun is this speed sufficient to escape the solar system? So for Part A, we're given that it's relative to the Sun, and that's basically about it. They ask us to find the escape velocity. So what we do, if we know that it's relative to the Sun, it's good to have the values of the Sun, such as the mass is equal to 1.99 times 10 to the 30th kilograms, and that the radius of orbit from the Earth to the Sun is 1.5 times 10 to the 11th meters. And of course, we already know that the universal gravitational constant, which g, is 6.67 times 10 to the negative 11th. So, the equation for the solar escape, or velocity of solar escape, is the square root of 2 times the mass of the Sun times the gravitational constant divided by the radius of orbit, which is from Earth to the Sun. Plugging in the values that we have above, it comes out to be this equation. If you were to plug that into your calculator, you would get this in units of meters per second. And to simplify it, you would shorten it to 42.1 kilometers per second using the conversion of meters to kilometers of the factor of 1,000 to get this answer. So in Part B, you're given that the maximum velocity is 125,000 kilometers per hour, and they ask you to find the distance from Sun to escape the solar system. So you just you let r, the radius of orbit, equal to, again, the radius from Earth to the Sun, and then you add in a value of x, which represents the variable distance from the Sun, and again, x's would be in astronomical units. So basically, the formula you would use is nearly the same formula that you used for Part A. However, there's a new added component of x at the bottom, which multiplies onto the radius. So in Part A, we found that this part right here, the original part, would be the 42.1 kilometers per second, and then because x is in the square root, it's divided by the square root of x, and the units are in AU. This is not a variable, it's just the units that x is expressed in. So they give you that the maximum velocity is 125,000 kilometers per hour. Now, normally when you're given something per hour, you convert it into seconds, and there's 3,600 seconds in an hour, so it's 125,000 kilometers per 3,600 seconds. And again, we go back to the earlier equation we found. So again, this is from right here. And then this is the earlier equation we solved at the beginning of Part B. And basically, it's just cross multiplication, and you end up with that. You multiply multiply the right side, and you end up with the number on the right at 151,560 kilometers. And then you divide both sides by the 125,000 kilometers. To get the square root of x is equal to that. And again, AU is the units for x, not of any variables. So you square both sides. You get your answer of x is equal to 1.47 astronomical units, which converted into meters at a unit conversion of approximately 1 astronomical unit is 1.5 times 10 to the 11th meters. Would get you 2.2 times 10 to the 11th meters. And that's your answer for Part B.